Thank you very much.
You're welcome.
Nice meeting you. Good afternoon from my side as well. My name is Bikas. I work as a research engineer at the Laboratory for Manufacturing Systems and Automation in University of Patras, that's located in Greece, for the ones of you that don't know it. And we are going to talk about something a bit different from what we have already seen. How we can use a race car and how we can use automotive technology to get students accustomed with not only engineering and automotive engineering, but also with 3D printing. This whole thing is based on a concept that we call the teaching factory. What is the teaching factory? It is something that originates in the concept of learning hospitals. What we're trying to do is essentially connect young engineers with manufacturing firms, because usually education, university education specifically, is something that's a bit cut off from actual industrial environment. So what we're trying to do is get students to learn through practicing theory, through getting to face real-life problems, and through presenting them challenges that will open up their minds and get them start thinking in a very original way. This concept has been used in our laboratory for Manufacturing Systems and Automations, quite a lot through these years. Here we do have connected classrooms with industrial shop floors as a two-way communication channel. The first step is flowing information from the industry to the classroom. So engineers and production engineers and people that are already accustomed to that transmit the information about their daily problems, and young engineers act as knowledge receivers. On the other hand, we do have flow of information from the classroom to the industry. New ideas, new concepts generated by young people are being transmitted to the industrial, to the established, let's say, engineers. And sometimes this new concept and new way of thinking solves problems that experienced engineers could not solve on their own. So we do have both sides benefit from such a communication. Of course, through all this, we get a series of skills and competencies for the students. And this is due to the fact that they put their imagination, their academic education, and everything that they have learned so far into practice through these projects. A very characteristic example of this whole thinking process is the Formula Student competition and the Formula Student project. What is Formula Student? Formula Student is a student engineering competition running worldwide, held annually in several countries with participation from university teams from all over the world that design and build their own small-scale Formula-style race car. The competition places a series of limitations on the car design, not so many in order to have completely same designs from everyone, but open enough to allow creativity. The target is to build a prototype for evaluation. This prototype is intended as a prototype of small-scale production with the intended audience of weekend non-professional racers. The competition splits into two big parts. It's the static part and the dynamic part. On the static events, as the word implies, we just present our design to people from the industry, explain the whole design process, the whole engineering process behind the car, and how the people of the team work together to achieve their goals. At the same time, we do have evaluation in terms of cost and manufacturing, so the product must be easy to manufacture, easy to maintain, but also be costed and cost something reasonable for an amateur weekend racer. And then the product that we have designed and we have prototyped has to be sold. So we are also trying to sell it during the business plan presentation. Then we do have the dynamic events, which is the actual fun part for most of the people taking part of the competition. It consists of 4 different races, let's say, which evaluate the dynamic performance of the car. We do have the acceleration, skid pad, autocross, and endurance. during the endurance race, which is 25 kilometers, and it actually tests a lot the reliability and the robustness of the solutions developed by the students, it is also tested the energy consumption and energy efficiency of the vehicle. So what we see is a competition that tests many different aspects of product design and car design, and of course this means that there is no single right answer to the problem: create a small single-seater race car for an amateur racer. Through these, we have about 170 students coming through the team. I have to note here that the team it exists at the University of Patra since 2002, so we are there for 15 years. Of course, the team is constantly changing and constantly updating with new students. Through that competition, through the different challenges that these people face, they develop a multitude of skills, such as teamwork, respecting deadlines, delivering under pressure, being able to present to a wide audience, get sponsors, get funding. So besides the actual technical training and the actual technical skills, they also develop a set of non-technical abilities that are very, very useful for their future careers as engineers. Of course, this whole exercise, besides the skill set development, also forms strong bonds between academia and industry, especially in the automotive sector. As already mentioned, the team is there since late 2001, beginning of 2002, so we have been there since 15 years. And throughout these years, we have competed in a series of worldwide competitions, like in Formula Student UK, Germany, USA, Italy, and Czech Republic. And over the years, managed to getting a lot of first places. We were the first team that started in Greece, the first team to actually starting playing with some more advanced material, especially if we talk about students. And the first team, and we're really proud of that, in Greece, and actually one of the very first people in Greece, managed to develop an all-electric vehicle back in 2011. And the only Greek team so far that ever managed to win the first place overall in the competition. A feat that we also repeated this year by also winning the electric class at the UK competition a few months back. A few words about our latest creation. This is what we call the UoP 5E. It is fully electric. It's a fully electric race car. Its weight is 2,013 kilos. Power is about 80 kilowatts, and maximum torque is 830 Newton meters. We have an acceleration from 0 to 100 kilometers in 3.1 seconds, and the top speed is around 120 kilometers per hour due to the maximum limitation of the competition. A few technical characteristics. I won't stay here for long. I just want to highlight that despite the fact that we have a vehicle built by students, these cars are fairly high-tech for what they are. Let's talk a bit about additive manufacturing now. What is additive manufacturing, and how can it be of benefit for Formula students? Additive manufacturing, the most widely known definition, is that it's the process of joining materials to make objects directly from 3D model data, usually layer upon layer, as opposed to subtractive manufacturing. This gives a series of advantages over traditional manufacturing methods. The most important here is the ability to deliver parts of very intricate and complex geometries, and the whole increased design freedom grants us a lot of opportunities to also reduce the weight, but also in some cases reduce the cost of prototyping, because there's no need for specialized tooling and specialized molds. Therefore, this makes additive manufacturing an ideal tool to create unique products that can be manufactured at low volumes in a very efficient way. So far, how we see additive manufacturing being used at Formula Student, we have seen, first of all, to use additive manufacturing as a physical prototype, as a real-life CAD. So teams usually test build some parts and see if they fit correctly in their cars, or if they look as they intended to. The second one is non-structural parts. We see quite a lot of these also in the automotive sector. There are parts that are functional, but the loads on them are very, very low. Usually, this includes ducts for a lot of purposes. Very interesting application is the gray part that you see here. Oh, sorry about that. The gray part that you see here, which is an air to water separator, it is being used for cooling of battery packs in electric vehicles, and is used as a trap to not let water in the battery pack. And then we do have actual load-bearing structures, which are very, very interesting because they allow for massive weight reduction potential. Here, we can take a brief look on where we used additive manufacturing on our latest race car. All the parts that you see highlighted in red are actually parts that are being built through additive manufacturing and 3D printing technologies. These include driver controls, so dashboard and steering wheel handles, functional ducts for cooling, housings for electrical components, such as some tractive system lights that are necessary mandated by the rules, but also some parts that we needed, for instance, some ribs on the aerodynamic devices, some high voltage parts, some parts for high voltage connectors, which do not allow the connectors to be plugged in a different way. So we are constantly expanding the use of additive manufacturing. And this comes to the first topic I already mentioned. It is very important for us, for young engineers, to find out themselves what additive manufacturing can offer in such a field. Let's talk a bit now about something we are currently considering for our next car and something structural. The potential for lightweight design through additive manufacturing. Why is low weight so important in Formula Student? It is important because of the second law of Newton, of course, and because for us, power is restricted by the rules at 80 kilowatts. So the only way to actually create a car that is faster is creating a car that is lighter. And in order to if you do so, that also means that you have also decreased energy consumption and decreased wear on normal parts like bearings and brakes and tires and everything. Also, for us, reducing the unsprung mass is even more important. Less unsprung mass means that the dampers have less work to do. That means that less heat is generated and the operation of the dampers is less affected throughout the race. Therefore, the ideal parts to demonstrate topology optimization, algorithms and logics, and also manufacturing through additive would be suspension components. The component that weight is not the only thing that we have to keep in mind when designing these parts, though. Stiffness is even more important when we talk about a race car, and therefore, if we are talking about suspension components, we need them to be stiff enough in order for the suspension to be able to maintain the kinematics that were so carefully analyzed and selected in order to have the maximum performance. So we do have two targets: maintain a high stiffness and at the same time reduce the mass. These two targets at first seem quite contradictory, and people are trying to design their way around it quite a lot. But additive manufacturing here offers a lot of potential. A characteristic example for such parts would be the suspension upright. The suspension upright is what actually holds the wheel in the car, what actually connects the wheel and the wheel bearings with the rest of the suspension system. So far, we do have a few different approaches by a few different teams. The first one, and the most obvious one for a Formula Student team, is used milled parts. These start usually their life as a big block of material, and typical subtractive manufacturing, typical milling. What it does not allow is for hollow spaces. So usually, if you want something to be very stiff, it usually ends up heavier than expected or heavier than necessary. The second approach that is quite popular is using, again, milled parts, but split them in half in order to be able to create hollow spaces. In that case, we do have, again, same technique for manufacturing, but we also need very high tolerances. And the fact that we need hollow parts also leads to a very high amount of wasted material, which doesn't make much sense. The third one would be gravity cast parts. It is a technology that is quite available to most teams nowadays. However, casting creates different problems altogether. Special tooling needs to be made. Usually, due to porosity, we do have quite a lot of scrap parts in that case, so the cost is prohibitively high. Additional heat treatment usually needed, and the minimum wall thickness achievable usually by casting is not that low. Fourth approach is fabricated parts, sheet metal fabricated parts. Usually teams go and design their uprights as a sheet metal structure, and they're usually welded together. This means that specialized jigs are needed, and most of the time these parts get also extensively distorted by the heat of welding. A different approach would be using additive manufacturing for these parts. And what we did here is we took the case of a rear upright as it was designed for milling initially, and tried to redesign it in order to be able to manufacture it with additive manufacturing in a way that makes sense. You can see here some areas that are the load-bearing areas, the surfaces where the bearings sit, and the areas where the suspension components connect to each other. Also, these two connections are the connections for the brake caliper. We have identified the loads through testing of the cars through data acquisition system. So we knew the exact maximum loads we expected. So what we did is setting a target, as target the minimization of mass, but at the same time to maintain the targeted stiffness so the suspension can operate in the way that it was intended to be. The loads were configured in the software that we used. This is a software made by a company called Beta. It's a Greek company. And we use their topology optimization suite for that specific reason. And we also then defined the areas that could be redesigned by the program. As you see here, the areas that are included are only the blue ones. Several areas were excluded due to actual design constraints because this part has to fit an already existing car. And after certain boundary conditions were set and the maximum number of iterations in order to solve the problem in a given amount of time, the whole iterative topology optimization analysis were run. And here you can see the results. As you see, there are 6 main redesigned areas. The weight was able to be reduced by 20%, which is quite significant for such an upright that was already optimized for milling beforehand. And some stress levels that we noted that are quite raised were offset by the better stress distribution, more uniform stress distribution inside the material. Also, we see that we do have a small increase in maximum deformations. That means a small reduction in stiffness, but this is quite negligible. This work has also been published in a paper. You can see right here. As a conclusion, we saw that when compared to CNC milling, we would be able to manufacture this part 20% lighter in a comparable process time based on data given by EOS than what we actually did by milling and by setting up the part. Please note that the process time here for milling includes setup, while the process time here for additive manufacturing does not include post-processing or machine setup. However, we can see that for us, time is quite comparable in those two cases. Concluding, we see that additive manufacturing offers a series of benefits for us, allows less material, allows less weight, and the time to produce both parts is quite comparable, although the costs might be quite different. that would be all. For more information, you can either send me an email or refer to the website or social media of the team. Thank you very much.